Welcome. Today we're diving into the world of ensemble learning, a powerful approach in machine learning that combines multiple models to achieve better predictive performance. Imagine you're working on a complex problem. Sometimes a single model just isn't enough. That's where ensemble methods come in. By leveraging the strengths of several models, we can reduce errors, improve accuracy, and create more robust solutions. Throughout this lesson, we'll explore the main ensemble techniques, bagging, boosting, and stacking, and see how they're used in real-world scenarios. We'll also touch on frameworks like TensorFlow and Keras, which make implementing these methods easier. Let's get started by understanding the basics of ensemble learning and why it's such a game changer in data science. Ensemble learning works by fitting two or more models to the same data and then combining their predictions. The idea is simple. Instead of relying on a single model, we use a group of models called base learners to make decisions. These base learners can be of the same type, homogeneous, or different types, heterogeneous. For example, in a healthcare scenario, detecting melanoma with just one classifier might not be reliable. By training multiple models and combining their outputs, ensemble learning boosts overall performance. The combined model, often called the meta-learner, is usually more accurate and robust than any individual model. This approach is widely used in business, healthcare, and even social media to enhance predictions and minimize errors. Let's look at the main categories of ensemble learning next. Ensemble learning techniques are broadly classified into two categories: parallel and sequential. In parallel ensemble methods like bagging, all base learners are trained independently and simultaneously. This independence helps reduce variance and is ideal for problems where data samples can be processed in parallel. Random forest is a classic example. On the other hand, sequential ensemble methods, such as boosting, train models one after another. Each new model focuses on correcting the errors of the previous ones, which helps reduce bias and improve accuracy. Eta boost and gradient boosting are popular sequential methods. The choice between parallel and sequential depends on the problem, data structure, and computational resources. Understanding these categories is crucial for selecting the right ensemble strategy for your project. Bagging, short for bootstrap aggregating, is a popular parallel ensemble method. Here, multiple weak models, often decision trees, are trained on different random subsets of the data. Each subset is created using bootstrapping, which means sampling with replacement. After training, the predictions from all models are aggregated, usually by voting for classification or averaging for regression. This approach helps reduce variance, increase accuracy, and minimize overfitting. Random forest is a well-known bagging algorithm. Bagging is especially useful when you want to stabilize predictions and handle noisy datasets. However, it can be computationally intensive and sometimes less interpretable. Still, its advantages make it a go-to method for many machine learning tasks. Boosting is a sequential ensemble technique where each model learns from the mistakes of its predecessors. The process starts with a weak learner, and each subsequent model focuses more on the data points that were misclassified previously. This is done by adjusting the weights of the data, so harder cases get more attention. Over several iterations, the ensemble becomes a strong predictor. Popular boosting algorithms include Eta boost, gradient boosting, and XGBoost. Boosting is highly effective for reducing bias and improving accuracy, especially in complex datasets. However, it can be sensitive to noisy data and may require careful tuning. The key takeaway is that boosting turns weak models into a powerful ensemble by focusing on errors and learning iteratively. Stacking or stack generalization is an ensemble method that combines predictions from different types of models, heterogeneous learners. In stacking, base models are trained in parallel on the same dataset. Their predictions are then used as input for a second-level model known as the meta-learner, which makes the final prediction. This approach leverages the strengths of various algorithms, making the overall model more robust and accurate. Stacking is commonly used in competitions and real-world applications where maximizing predictive performance is crucial. Unlike bagging and boosting, stacking can handle both homogeneous and heterogeneous models, offering great flexibility. It's especially useful when you want to blend the insights of different algorithms for superior results. Wrap-up: ensemble learning is a cornerstone of modern machine learning, enabling us to build models that are more accurate, robust, and reliable. Whether you're using bagging to reduce variance, boosting to minimize bias, or stacking to combine diverse models, these techniques offer powerful tools for tackling complex data challenges. Frameworks like TensorFlow and Keras make it easier to implement these methods in practice. From healthcare to business intelligence and social media, ensemble methods are driving innovation and delivering better predictions every day. As you continue your journey in machine learning, mastering ensemble techniques will open up new possibilities for solving real-world problems with confidence.